So images can be formed by refraction as well as reflection, like off of a mirror. Because all we need is for the light rays to converge at a point after they refract. So let's say we have two different materials. Say this could be air and this could be water. And we're going to look at refraction at a spherical boundary, which just means the boundary, instead of a flat line, is going to be curved like a circle. And so again, like a mirror, we have a center of curvature and a radius of curvature. So here you can see two example rays that come from this object. So this ray is already along the normal line. It's going through the center of curvature, so it is not deflected through refraction. So it just continues on a straight line through the center of curvature. And then this ray, it hits at an angle, and so since this second material has a higher index of refraction than the first, it's going to bend towards the normal line, given by Snell's law. And then these rays converge at a point, and that's where the image is formed. So you can see the image is real and inverted. And remember, we had the mirror equation for mirrors. Well, in this case, refraction through a spherical boundary, the same equation is given by this. So Na, which is the index of refraction of the first material, over S, the distance the object is from the boundary, plus N of B over S prime, equals the difference in their index of refractions over the radius of curvature. And the lateral magnification, the image height over the object height, is given by negative Na S prime over NBS. And these equations aren't really important. The important part is that we see how an image can be formed by refraction through a boundary. Because we're going to use these principles, of refraction to look at lenses. And so a thin lens is consisting of two spherical surfaces, and they are close enough together so that we can neglect the distance between them. In other words, we can ignore the lens's thickness. So there are two big types of thin lenses. The first is a converging lens, which causes incoming rays which are parallel to the optic or principal axis to converge at a point. And this point is called the second focal point. A lens has two focal points, one on either side of the lens. And again, the focal length is the distance from the center of the lens to each focal point. And the focal length is actually always the same on both sides of the lens, even if the lens is not symmetrical. And so for a converging lens, the focal length is defined to be positive. And a lens like this is also called a convex lens, but that might get confusing, because if you remember, a convex mirror causes light rays to diverge, not converge. So I like to call it a converging lens, not a convex lens. So the other type of lens is a diverging lens, which causes incoming parallel rays parallel to the principal axis to diverge. And they appear to diverge from this point over here, the second focal point. So we've kind of switched the second and first focal points. So you can think of the second focal point as where the light rays appear to, or actually do, diverge from after they pass through the lens. So for a diverging lens, the focal length is defined to be negative. And again, this is sometimes called a concave lens, but that's confusing because a concave mirror causes light to converge, not diverge. And so you can tell if a lens is converging or diverging by looking at its thickness at its center compared to its edges. So if a lens is thicker at its center than its edges, it's a converging lens. and if the edges are thicker than the center, it's going to be a diverging lens. So just like with mirrors, when we make a ray diagram for a thin lens, there are certain rays that are always going to be easy to draw. And these diagrams are kind of sketchy, but you can get the main idea. Just don't pay too much attention to them. So the first is a ray that it's parallel to the principal axis is going to converge or appear to diverge from the second focal point. And so obviously in a converging lens, it actually does pass through the second focal point, and in a diverging lens, it's going to appear to come from the second focal point. Now the second ray is if a light ray passes through the center of the lens, then it's not going to change direction. It's just going to keep going straight, because it's as it hits the lens, it's refracted a little, and then it's refracted a little as it exits the lens, and it turns out these two changes kind of cancel out, so it just keeps going straight. And the last easy ray is if a ray is passing through the first focal point on its way to the lens, then it's going to emerge after the lens parallel to the principal axis. In a diverging lens, this means that if the ray is appearing to head towards the first focal point, as you can see here, but it hits the lens before it actually passes through it, it's still going to emerge parallel to the principal axis. So of course, after you draw these three rays, then you're going to see where they converge or where they appear to diverge from. And then that's where the image is going to be. So you can see in this converging lens, the image is real and inverted. And in this diverging lens, the image is virtual and upright. And the same basic equations that we used for mirrors can be used for thin lenses. So we have this guy again, 1 over s plus 1 over s prime equals 1 over the focal length. And then also the magnification is negative s prime over s. And again, we use the same sign conventions. You look at if the image or the focal point is on the same side of the lens as the outgoing light. And if it is on the same side, then it's positive. If it's not, then it's negative. And the focal length is still half of the radius of curvature. So we have one more thing, the lens maker equation. This is going to give the relationship between a lens focal length, its index of refraction. Remember, it's usually they're made out of glass, so they have a different index of refraction than the air, and the two radius of curvature of its two surfaces.